Recording is rolling. This is Thursday, September 30th, last day of Thursday. Remind you guys, or last day of Thursday, last day of September. Remind you guys that your dynamics quiz is due tomorrow. Remember that's open notes take-home quiz you guys have had for almost a week now. Also, your impact forms. Now, most of you guys, I think, have already turned in those impact forms. If you haven't today, feel free to pop them in the Great Trade. If you haven't turned it yet, then tomorrow is the final day for those. We're almost at the end of this week. So today, you guys get a new concept called centripetal force. And this comes with a whole new formula that I'm going to let you guys discover empirically using science and measurement. So your setup is going to involve a PVC pipe, a string, a couple of Play-Doh canisters, and I've got this rigged up. So that picture I drew is, it's this right here, a couple of Play-Doh canisters, PVC pipe, string, and you're going to swing this top Play-Doh canister in a horizontal circle so that there's a certain type of equilibrium, but, well, now here's where things get kind of fishy. Now, this weight down here, this could be in true static equilibrium, right? One force down, it's weight, one force up, the tension in the string, and it would have zero net force, right? But what about that top Play-Doh canister that's swinging around in a circle? Would that be in true static equilibrium? Suppose this radial size is staying the same. Is this an equilibrium? Well, maybe I have to go back and talk about something a story that keeps coming back in this class, which is if you're in a car, can you feel how fast the car is going? Yeah, the answer is no. Remember, all velocities are relative. Same thing in a plane. Like the Earth is spinning right now, and the latitude that we're at, we're going almost 1,000 miles an hour straight east. You can't feel that, right? Because velocities are all relative. But you can feel three things in the car. You can feel speeding up, like gas pedal. You can feel slowing down, hit the brake. And we've covered those extensively. What we haven't brought in yet, and we're about to starting today, is what's the third control? Steering wheel. So there's the force due to turning. Now, why do you need a force turning? Because remember Newton's first law of motion. One of the things it says is that if something is in motion, it wants to just keep moving in a straight line. It's constant speed. Now, this top Play-Doh canister, could it be going constant speed? Constant speed. Is that okay? Yeah. Say you're in a car and you might be turning around a turn. You might be going a constant 30 miles per hour. That could be constant speed. Is constant speed the same thing as constant velocity? Not necessarily, because you might be doing constant speed, but you might be changing your direction. And that means there's also an acceleration involved. Now, it's a special kind of acceleration that we're bringing in today called centripetal acceleration that's caused by some centripetal force. What force is actually holding this Play-Doh can, this top one, in a circle? Yeah, the tension in the string, which is also equivalent to the weight of this bottom bucket, isn't it? Ooh, see how this is all going together? Actually, you know what? I think there are 4 variables that you have to juggle that are working in concert with each other that fit in some tidy equation at the end of this lab. To hold this top bucket in what you might call a dynamic equilibrium. Sometimes you hear that. It's not true static equilibrium. There is a net force, and you guys told me it's the tension string that's pulling it inward. But maybe some dynamic equilibrium. See how if this is going in a circle, if you cut the string right here, doesn't this want to fly off tangent to its motion, like exactly along that beat path? But wait a few milliseconds with the string intact, and it's going to deviate from that straight line path. It's going to actually be pulled in. Yeah, that is the centripetal force. What is the centripetal force as a function of these 4 variables? We got the swinging mass up here. We got the speed that it could be going at, call it instantaneous speed. You might also call it tangential velocity, so we'll call it speed. You have this radial size, and finally you have this weight, which is creating the tension of the string, which is ultimately supplying the centripetal force that's pulling them. So if you call this like centripetal force, because that's where it's come from, what is centripetal force as a function of these other 3 variables? That's a question. Let's do a bit of quick hypothesizing. If you were to, you know what? Let me turn this around a bit too, because there's different ways to approach this lab, but the easiest way is to route everything through velocity. Let's think about velocity as being sort of a dependent variable, and then the other 3 could be independent variables, right? But only one at a time, right? So you guys see where this is going, which is that there are going to be 3 different versions of the lab. Okay, so I'm about to get to that in a minute. But quick hypothesizing. If you were to increase this weight at the bottom, say increase centripetal force, and leave these two, the radius and the swing mass, the same. Do you think you'd have to swing faster or slower to maintain dynamic equilibrium? If this weight's going up, how do you think you have to swing this? Probably faster makes sense, right? Right. So that's a good hypothesis. Now, I wonder if you could, is it a linear relationship? Is it some kind of root relationship? Maybe nail that down. How about this? What if you leave this weight and this radial size the same, but you change out the swinging mass? What if you make this swinging mass heavier and heavier? Do you think you have to swing faster or slower?
Slower.
Probably slower makes sense, right? Again, I wonder exactly what that relationship is, if you could quantify that. And then finally, this radial size. What if you leave the two Plato canisters exactly the same, like you never change out those masses at all? Okay. But this radial size, maybe over per trial, you make it longer and longer. If you have a longer radial size, do you think you'd have to swing faster or slower? Let me see, show of hands. How many think for a larger radius, you need to swing it faster? And he says for a larger radius, you need to swing it slower. Okay, so I'm seeing hypotheses going both ways on that one. So, so that'd be an interesting one to.
When you're saying like faster, slower, you're talking about velocity, right?
Yeah, the speed. Right? You know what? Actually, I think the reason you bring up that question is where this is eventually going to is there's actually different kinds of speed. So the speed I'm doing here is called linear speed, like meters per second. But you might, in the back of your mind, be thinking, what about like revolutions per second or revolutions per minute? I've never mentioned that in class before, have I? Right? That's a different kind of velocity. It's called angular velocity, right? Or rotational velocity. So eventually we'll talk about that. And depending on whether you're talking about linear velocity or rotational velocity, you're right. You might actually get different answers to that hypothesis question. So some other things I want to point out. Notice that the swing one, I'm referring to its mass, but the hanging one, I'm referring to its weight. Now, you guys know those are different concepts, right? Like mass could be in, today we're just going to do grams, but weight, that's a force, that's a vector quantity that could be measured in like newtons, and today you can use millinewtons because the values are pretty small. Let's look at these lab papers. Now, I've got 4 different ones floating around. There are 3 different versions of the lab, and then, here, we'll do this one by one. Right, so, make sense of this table. I'll zoom in here. Let me show the camera up close. So, in case you're watching this on video in the future, and hold that there, you can take a screenshot, take a look at what's going on. Right. So, we have, see, the hanging mass. Okay, so record that number maybe in grams. I've got, I do have some scales back there and a triple balance beam, but I'll tell you what, if you have trouble accessing those, here's a less scientific but quick and dirty way to do this, is that the small Play-Doh canisters are about 6 grams each, and the heavy ones, the large ones, are about 32 grams each, pretty close to your Hot Wheels cars. And then if you take these lab weights, you can just add those two. So each of these are 20 grams. So this is 20 grams, 20 grams, 20. If I loaded these in there, I could just add those weights, okay, do something like that. More scientific ways, you do direct measurement, but if you want to do it the other way, you'll get numbers that are close enough to make this lab work really well. All right. Next column, weight hanging. Hey guys, how do we go from mass to weight? Multiply by gravity field, like 9.8 meters per second squared. Or if you use 10 meters per second squared, that's fine. And then that would also convert from grams to millinewtons at the surface of Earth. Right? So go ahead and do that. The swinging mass, you can do in grams. Take the reciprocal of that for reasons that you'll see by the end of the lab. Radial size in meters. Now notice that 3 of those columns I put in bold. You guys see the weight hanging, the mass swinging, and the radial size? That's because each one of those could represent one of the independent variables, the way that we're approaching this particular lab. And this particular paper that I have up here, notice the hash marks down these middle columns. That means if you have this exact paper, I want you to keep the swinging mass and the radial size controlled. So you're only dealing with the independent variable of the hanging weight, except versus if you have this page with the split hash marks, your independent variable would be the swinging canister, and you leave these 2 controlled. And if you have this page, then you'd be changing out the radial side every trial, but leaving the 2 Play-Doh canisters untouched. Yep.
Mine doesn't have any hash marks.
And if you have a completely open table, that's like having O negative blood. You can just give it to whoever. Yeah. How about these other? So it just makes it easier for you to join groups. So try to find a group that everybody has the same type of paper. If you need to trade them out, that's all right. How about these other columns? So, time step 10, what do you think that refers to?
Is that how long it takes to do 10 swings?
Yeah, the time to do 10 revolutions. Now, why would I care about that? Well, because ultimately you're trying to figure out the one I haven't mentioned yet, which is this V, right? Can you guys think of a way to figure out what this V is? That's speed? Good critical thinking type question, right? I'll show you right here. So if you know the time to go around 10 times, and then you divide that by 10, then can you get the time of one revolution?
Yeah.
And then you guys know the purpose of doing this method is that also the error of starting and stopping that stopwatch would also be divided by 10. And then V, V's right here. You can calculate it. 2 pi r divided by t? Hey, what is 2 pi r? That's circumference of a circle. So, I see what's going on. So that'd be this distance, circumference of a circle, divided by the time that it takes to do that. Wouldn't that give you the instantaneous speed? Sure would, wouldn't it? And last column says to square that speed, just to help put the graphs together. There's a certain way to go about this lab that's the easiest way that, well, it'll make sense when we're getting to graphs. Okay? Any questions so far? Okay. So a few more things I want to tell you. One is that this is one of those labs that if you're really good with the stopwatch, like starting and stopping it very accurately, and also if you're really good at keeping this radial size controlled, one way to do that is to tape a little flag to this string down here and just make sure the flag doesn't move up or down. Right? So you could do something like that. So if you do all that, if you do this lab really well, then when we get to the graphs, it'll definitely show up in the graphs. And you have really pretty graphs, and then this lab will work out really well. On the other hand, if you're really sloppy with keeping this radial size accurate and so on, then that will also show up in the graphs, and the graphs will be kind of messy. Hey, do you want this bottom plate of bucket to bump up against the bottom of this PVC pipe? No, because that would introduce other forces that would throw this off. Do you want to grab this bottom bucket and hold on to it? No. The idea is that you want the weight itself to provide the force. So there's a measurable weight that's providing the centrifugal force. Yeah, Eddie?
Don't we have to swing it ourselves though?
Yeah. Here. Oh, okay. So actually, that's a perfect segue to what I was gonna do a demo for you guys. Before I switch this camera around, one more thing is that I'm gonna have you guys do a AP style write-up. I don't have the printed page, but if you need paper, then I've got blank paper for you guys. So it's the same 5 questions. Question, measuring tools, data gathering procedure, analysis, conclusion. And I have write-ups for any of the 3 experiments that you might be doing, and I'll have you guys grade yourselves, but like we normally do with those. Let me just turn the camera, and I'll do an example for you guys. Okay, so got the PVC pipe, string, couple Play-Doh canisters. Okay, so hey, look at this. See how the orange canister is in static equilibrium? Okay, and then the top one, well, the radial size is constant. Okay, I might tape a little red flag or little flag right here, just make sure it doesn't move up or down. Okay, and you might do something like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then somebody would time that, and let's say it comes up to like 4.5 seconds, like 4.5 seconds. How much time would it be for one revolution? 0.45 seconds, right? You just divide by 10.
Why'd you start on 0?
Yeah, well, guys, why did I start on 0? Yeah, right, because the 0 is the starting point. If you start counting at 1, and by the time you get to 10, you will only count at 9 revolutions, so it wouldn't be completely accurate. Right? Yeah, so that's a great question too. All right, so I think I told you guys everything I need to tell you. I will leave this up here, and you guys got the rest of the class to gather all your data. Tomorrow, we'll put the graphs together as a class.
Oh, and then
So you're-
All right.